So the first 4 examples are all we are looking at in 4.4. The pages after that, you will actually see there are applications. So these are similar applications to what we had seen in the past. There's a radioactive dating example, and I think there's Newton's model of cooling example. So this was just to show you how some different examples would look like, but again, nothing new. Maybe Newton's is new, but the format is still very similar. So we're just doing these 4 examples so you can kind of know how to solve these logarithmic and exponential equations. So let's start with this first one here. It's giving you log of 2x plus 1 equals 3. How do you think we can go about when they're saying solve? Of course, that means they're asking us to find x here. Can we solve it the way it's given to us, or do we need to do something?
Could you distribute the log and put it like
No, unfortunately, no. That's not how it
We're
works.
rewriting it, aren't we? In a different format?
Yeah, you actually again convert it into exponential format because, as Amy said, you can't really distribute that log, and even let's say we could, which we can, it still wouldn't really get us to a solution. So here, convert it to an exponential format. So again, just to remind you of how that conversion happens, if you have log of base a for some number x equal to y. So when you're converting it from log to an exponential format, we take that base a raised to the value of y equals x. Okay, so that's how the conversion happens, and that will be something you guys definitely need to remember. So what do you think happens with the log here then?
2x plus 1 equals 10 over 3.
Yeah, so your base is 10, raise it to the exponent of 3, and it will always equal that value of your logarithm, so 2x plus 1 is what it will equal to. So what is 10 to the third? No. 1,000, yeah, 1,000. Basically, the easiest thing with 10 to any exponent is this is 10, and the 3 tells me 1 is followed by 3 zeros, basically. Okay? So 1,000. Okay, can you tell me what that x value will come out to be? No decimals, leave it as a fraction.
999 divided by 2.
Yeah, very good. So start by subtracting that 1, which gives you 999 equals 2x. To get x by itself, divide both sides by 2. And that's it. Okay, like I said, if they ask you for a decimal answer, you can put it. If they say leave it as a fraction in reduced form, then that's your answer. Okay, take a second and tell me what do you think is going to happen on number 2 here. Log of x minus 1 plus log of 3 equals log of x minus log of 4. Something we did in the last section. Any clues? No? You sure?
Combine them both.
Combine them using what?
product equal and the quotient?
Yeah, so the plus sign between the 2 logarithms will tell us that's going to be the product rule. The minus sign is telling us quotient rule. Remember, the only thing we always want to make sure when we're combining our logarithms into a single log is that our bases on all the logarithms are same. And of course, you can see these are all common logs. So on the left-hand side, we're going to use product rule. So product rule, of course, that means you're multiplying x minus 1 with 3. Quotient rule, of course, is division, so that's going to be log of x over 4. So that's how we combine these into single logarithms. On the left-hand side, since you've got x minus 1, that whole quantity multiplied with 3, go ahead and distribute the value of 3 inside the parentheses, which will, of course, end up giving us, what is that, 3x minus 3. And log of x over 4 on the other side. And we had briefly talked about this property. Do you know what happens next?
Just get rid of the logs, right?
Yeah, this is where the one-to-one property of logarithms is coming into play. So what's happening is, again, since I have the same base 10 logarithm on both sides of my equation, the one-to-one property basically says if your bases are the same, then the values are equal to each other. And I think this was again in 4.3, I think we had talked about the one-to-one property, or maybe 4.2, but you can go back and look at the one-to-one property for logarithms. So again, since they are the same base logs on both sides, you can basically just say 3x minus 3 equals x over 4, and this is by the one-to-one property. Okay, can you go ahead and tell me what that x value will come out to be? Okay, what are you doing?
I multiplied each side by 4. Because
Yeah.
it's dividing by 4, so
Right.
I just distributed the 4.
So that would be the easiest thing to do, is get rid of that denominator. So go ahead and multiply both sides by 4. And of course that would mean we end up distributing the 4 again on the left hand side inside our parentheses. Okay, so you get 12x minus 12, now what?
And subtract the 12x to get it over the.
Okay, get your x on the same side, which will give us negative 12 equals negative 11x. Very good.
So you divide.
Get x by itself, so divide both sides by negative 11. And what's our final answer?
It's going to be 12 over 11.
There you go, 12 over 11. Again, leave it as a fraction. So this question used product rule, quotient rule, and one-to-one property. And this is kind of what I was hoping to show you guys, because up until now, we've actually just dealt with one property at a time. We've rarely brought so many of these properties together. So that's actually what's happening with these examples in 4.4, is just we're kind of building up on everything that we have done. And so you can see sometimes you need to bring multiple different rules and stuff together to be able to solve one given example. So questions on number 2. Okay, our next 2 examples are dealing with exponential equations. So this will actually be very similar to what we had done with the base change formula last time. So this guy here is giving us a base of 1.05 raised to the power of 3t equals 8. So do you have a starting point? Where do you think this one we should start with?
Can you change it? Like put it into the log equation, or?
Yeah. So like I said, kind of like a base change formula, but we're not directly applying the base change formula, though you can do that here. So either take a log on both sides of your equation, so you can use log or natural log, either one of them will work. Just don't include both of them in the same example. Or if you remember the base change formula, you can go directly into that. So let's go ahead and actually use, I'm going to use natural log. Remember, you can also use log here and it will be fine. So all I'm doing is applying a natural log on both sides of my equation. And really the main reason we are using log or natural log is so that we can take our exponent using the power rule and bring it down to the base level, because again, obviously we're solving for t. We want to get t by itself. So this will end up giving us 3 times t times natural log of 1.05 and equal to natural log of 8. Now we're trying to get t by itself, so what should we do?
Divide by natural log.
And
Divide by
so basically get rid of everything else but t, right? So divide by the natural log of 1.05, but at the same time, I'm also bringing the t down with it. So you're basically dividing by 3 times natural log of 1.05. So 3 will cancel out, the natural log will cancel out, leaving us behind with just t equals natural log of 8 over 3 times natural log of 1.05. These guys we will be rounding to 4 decimal places, so just be careful of how you type this in. If your calculator does parentheses, again remember to close your parentheses around log of 8, and if you're typing all of this at the same time, make sure you're putting parentheses around your denominator also. So what does this guy come out to be with rounded to 4 decimal places? $42.62. Something has been typed in incorrectly. Shouldn't be that high.
14.220.
4 decimal places. 14 point?
14.2066.
No. Check your rounding again.
600.
Yeah, 2067. Be very, very careful with your rounding, because that's really the place where you lose points for these, okay? So 14.2067, again, like I said, if you need to close parentheses after the natural log of 8, do that, divide. If you're dividing by the whole thing, then put your 3 times natural log of 1.05 in parentheses, or do it in 2 steps. So first you can divide by 3, whatever answer you can get, divide that again by natural log of 1.05. Obviously, same kind of thing happening on number 4 here, because again, both my variables are in the exponent, so which means we need to use logarithms again to bring it from the exponential to the base level. Since we used natural log in this example, let's go ahead and use log for number 4 so you can see it works with either or. So again, the main reason for using logs is using the power rule to bring those exponents down to base level. Again, x minus 1, the whole thing, since it was in our exponent as one value, when you bring it down to the base level, put it in parentheses. So we know that that entire thing was part of our exponent. And then on the right-hand side, of course, you will have x times log of 2. Now our goal, of course, is to get x together and get x by itself. So think of log of 3 as a constant value, because it is one real number value. So just imagine if you had x minus 1 multiplied by 3. We would go ahead and distribute that to get our solution. So that's the same thing that's happening here. Log of 3 is one number. So to get our answer, the first thing we actually do is start by distributing that inside the parentheses, which will end up giving us x times log of 3 minus 1 times log of 3, of course, will be just negative log of 3 equals, x times log of 2. All right, so once we distribute that number on the left-hand side, at this point, we've got one x term on the left, one x term on the right. Again, think about this almost like if this was 3x and that was 2x. We, of course, want to get our x on the same side. So let's start by subtracting this guy here. Negative log of 3 so these guys cancel out. We are left with negative log of 3 on the left-hand side. And then I've got x log of 2 minus x log of 3. Okay. So both my terms on the right-hand side have an x on it, which is what we wanted. We got them on the same side. So since both of them have that common x term in it, we can basically factor it out like we would, again, if you had 3x minus 2x, technically we could have subtracted that to get an x, but we cannot do the same thing with logs. So for this case, we're basically just bringing the common term outside as our greatest common factor. So bring that x outside, which leaves us behind with log of 2 minus log of 3. And of course, you've got your negative log of 3 on the left-hand side. And that's pretty much it. Now that we have x separated from our log terms, all we have to do is divide both sides by this whole expression log of 2 minus log of 3. These guys cancel out, leaving us behind with the x term. Okay, and then you can plug in this portion in the calculator. Again, guys, remember, since we have that whole expression on the denominator, put it in parentheses. And we're still rounding it to 4 decimal places. So what do you think we get?
2.7095.
2.7095, yeah, that sounds good. Lorexi, is that what you had? Yeah, all right, very good. So this one obviously is a little bit involved just because our x was on 2 different sides and we had to try and bring it together. So just go through the steps and let me know if you guys have any questions about this stuff. Alrighty, and like I said, that's the only page we're really working on. If you look at the other pages for 4.4, I'm giving you the example, but I'm also giving you the solution following right underneath the example. So you've got your radioactive dating example. I've got the solution underneath that. And your Newton's model of cooling, which also looks very similar in equation to that radioactive dating example. So they are both very similar. You will not have questions on those applications from 4.4. It's only going to be something similar to the first pages here. Alright, so that's section 4.4. 5.1, yeah?
Oh, I didn't get the packet.
You didn't get the packet? Okay, hold on a second.